Yeah, so welcome to this tutorial session on the molecular dynamics part of this course. And I hope most of you have could have had a chance to have a look at the handout. And so this is what we are here for. So to talk a little bit about this and to clarify things that are not so clear. Are there any questions? Something you would like to ask? So as always, don't hesitate to ask, because chances are your colleagues also have the same question. Hesitate to ask them. Is the okay, if there are no questions, then I just go through these slides again, and maybe as I go through the slides, maybe one, it's easier for you than to ask questions. I'm trying to do that now. Just opening the presentation. All right, I hope you can all see the slides now. And so that's usually what I do, a summary of the last lecture. And so, okay, starting from the full problem, full electron nuclear Schrödinger equation, we had two approximations that simplify things. One is the Born-Oppenheimer approximation. So that's two assumptions here. First, the relevant electronic state is just a single state, usually a single eigenstate of the electronic Hamiltonian. So that's usually the ground state. And the second approximation is that we assume that the masses are much heavier than the electron. And if you use this, then the full problem simplifies to the problem given in equation 1, where you go from the fully coupled problem to just the problem of the wave function of the nuclei. And you see a new quantity appearing, which is the potential energy surface, ER0, and the Tn is the kinetic energy operator of the nuclei. And this is still a quite difficult equation to solve. So if you're not interested in quantized nuclear motion, and you can change this and go to a classical description. And so this is what we have done in the last series of lecture slides. And that's usually a good approximation at high temperature and or high mass of the nuclei. And then you derive the classical equations of motion, means Newton's equation of motion, from the Schrödinger equation for nuclear motion. And so this is let's see. So this is so this is much easier. So all what you have to do, you have to calculate the forces at each classical nuclear configuration F, and then you have to integrate the equation of motions to get the trajectory, the classical trajectory of the nuclei as a function of time. So that looks looks very simple, but you cannot do that analytically because the force is nothing else than the derivative of the potential energy surface with respect to the nuclear coordinates -1. And so this derivative is not analytically available because the potential energy surface is very complicated. So you may have modeled this with sort of some harmonic springs or sort of some harmonic potentials, and of course everything is analytic, but in reality, you know, you have the interactions between the atoms are much more complicated. And so you have to, you don't have this analytically available. So you have to integrate the equations of motion numerically. And so these time-stepping algorithms, so these are sort of established methods to do that. And they are good because they have a relatively small error in the integration, meaning so you can use relatively large integration time steps. Okay, is there anything, are there any questions that you would like to ask about this? Okay. Then, okay, so then we had, we discussed that there are different ways of molecular dynamic simulation depending on how you calculate these forces, how you get these potential energy, the potential energy surface. And, you know, if you want to do, let's say, this, if you want to simulate chemical reactions where you break chemical bonds, and we're going to see a movie there later on. So then you have to derive this potential energy surface from first principles. And when you calculate this potential energy surface from first principles, you say you're doing, let's say, density functional theory-based molecular dynamics. And if you, you know, if you, for instance, want to simulate the motion of a protein, just conformational motion of the protein, and you don't break any bonds, so this can be relatively well described by classical force fields. And then you do classical molecular dynamics. So what I would like to continue with is the Born-Oppenheimer molecular dynamics, where you derive basically the forces from ab initio calculations. So now remember the Born-Oppenheimer MD. All what we have to do if we do MD simulation, we have to go from a nuclear configuration R to at time t to a nuclear configuration R at time t plus delta t, with delta t being the time step. And if you remember how these time stepping algorithms work, all what we need is actually the force on the nuclei at our initial position R of t. Now, this force in Born-Oppenheimer MD is, as I said before, is obtained from static electronic structure calculation. So static means you just have your nuclei at this given position R of t, and you solve the electronic Schrödinger equation for that. So that's usually what's done in your favorite electronic structure program. So this can be Gaussian or CP2K or quantum espresso or VASP or whatever. So they do this for you. So they calculate the total electronic energy at R of t, and also the derivative with respect to the nuclear coordinates, giving you the force. And I call this static because these programs, they do this for a given nuclear configuration. They don't move the ions, at least for this purpose. And this static nuclear configuration here, I denote with a prime, R prime, okay, so to make things a little bit easier in terms of notation. So this is what these electronic structure programs do, right? So they minimize the electronic energy with respect to the wave function, psi of r. You have the electronic Hamiltonian, which has the usual terms. And so there are several ways to do that, as we have seen. So you can do that either with Hartree-Fock theory or with wave function theory, or you can reformulate this in terms of density function theory, where you, instead of minimizing the wave function, you minimize an energy functional with respect to the electron density, which we see in the next slide. And this minimization process is equivalent with actually solving the ground state energy and the ground state wave function of the electronic Schrödinger equation, right? So this is always, so this is equivalent. Okay, so this is okay. So that gives us the total energy at this given configuration R prime, and so then we have to calculate the force, and the force is nothing else than the gradient of that energy with respect to the nuclear coordinates, evaluated at configuration R prime. Okay. Right. Are there any questions for this slide?
Hello.
Yes.
Hi. I'm Aidan. I think there might actually be a question more on the next slide, but if the because the calculating the forces seems to rely on it being an eigenstate from more the next slide. If that optimization isn't exactly to an eigenstate, does that cause issues in calculating the forces?
Yes, it does. There is, I mean, there is obviously then if it's not, well, it depends. I mean, if you use the Hellman-Feynman theorem and you don't have the, well, you never have the exact ground state wave functions. You don't have the exact forces. So okay. You still, in this case, you still use the Hellman-Feynman theorem, but there is a slight error associated with that, right? So because you don't have the exact ground state wave function.
Okay. Just to check, you don't, in general, always get the exact ground. You never get the exact ground.
You never. Function. I mean, that's right. You never get it exactly.
Okay.
Yeah.
Right.
So the force here. So this is as I said. So this is a actually a complicated object if you look at this, because it might involve well, it actually involves in the first, if you try to evaluate this, it would involve these nuclear gradients of these ground state wave functions, and this is sort of, if you like, a response property. How does the wave function change, the electronic wave function change as I slightly perturb the nuclei? Fortunately, due to that Hellman-Feynman theorem, you don't have to calculate that because these nuclear gradients of the wave function, they cancel out, fortunately. And so this is what I tried to explain in these following two slides here. And this is a much more general theorem. And if you apply it to forces, then this is a special case. So you can consider, let's say, any kind of Hamiltonian that just parametrically depends on a parameter lambda, and so then you have this eigenfunction of this Hamiltonian, not necessarily a ground state, and the corresponding eigenvalue E lambda. So in this last, so these are the assumptions, and then the last equation basically is the Hellman-Feynman theorem. So that tells you that this derivative of the expectation value with respect to lambda is equal to the expectation value of the derivative of the Hamiltonian. Yeah, so you can just drag this differential inside that bracket, so what you see is that the derivative of the wave function with respect to lambda does not appear anywhere. And so, so this is obviously extremely helpful for our task of finding the forces, because just imagine the lambda is one of our nuclear coordinates. Okay, so obviously this is a gradient, which is force gradient is of course 3n dimensional, but I mean this Hellman-Feynman theorem of course applies to each component of that 3n dimensional vector. So just, you know, one of these nuclear coordinates components is, let's say, lambda, and so obviously this psi r0 would then be our psi lambda. I mean, it depends obviously on lambda. The Hamiltonian, of course, depends on lambda, basically on the coordinates in here, because why is that? Because of course the electron nuclear interaction depends on the nuclear coordinates, well, as well in a trivial way, as well as the nuclear interaction energy. Okay, and so so you can just then one-to-one apply that Hellman-Feynman theorem to the force calculation, identifying lambda with one of your nuclear coordinates. Okay. So this kind of proof is very nice and short and straightforward. Are there any questions, something that's not clear here in any of these lines? No, that's good. Well, it's just very basic quantum mechanics here, each line. And okay, so as I said before, as we said before, so that was the questions, and obviously that assumes that you know the exact eigenfunction of that Hamiltonian, and so that's, you know, usually you don't have it. You often you can sort of right, if you do an electronic structure calculation now, so then you either, you know, if you do a Conchamp calculation, you build the Conchamp Hamiltonian with your orbitals, diagonalize it, and then you get output orbitals. And then you compare the output orbitals with the input orbitals, and if they differ, which they usually do, then you construct a new Conchamp Hamiltonian with the new orbitals, and then you sort of iterate this self-consistently until input is output up to a certain deviation. And this is typically a parameter that you can control. So usually in numerical schemes to get your eigenstates, so you can usually sort of iterate them sort of to arbitrary accuracy. So this is, you know, why actually this Hellman-Feynman theorem holds very well also in practice.
Sorry about the background noise, but can this Hellman-Feynman theorem be used to calculate pairwise forces? So if lambda is like the distance between two atoms, can you use it to calculate like you would normally have like a Lennard-Jones potential in classical molecular dynamics? Can you do pairwise forces that way?
Yeah, no, that's a good question. So if you do classical molecular dynamics, you don't need to use the Hellman-Feynman theorem.
Yeah.
I know where you're coming from, because
but I was wondering if you could.
In theory, you know, you could essentially do that. Yeah, for any lambda is any parameter, so you could you know, if you write down your you know, your Hamiltonian in terms of a distance difference rather than a coordinate, and it's also valid, because as you see in this derivation, nowhere you use what that lambda actually is, other than a parameter in the end. I should also say that. Yeah, sorry.
Sorry, I was going to say, I guess it might be tricky because you'll have to keep track of, because as the particles move, the distances will move, and then your Hamiltonian will constantly be going under lots of different coordinate transformations to go into those relative coordinates. I've just heard before that you can't use things like green cubo with sort of Born-Oppenheimer MD because because you can't calculate the pair of forces. That's all. That's what I was asking the question.
But I mean, it's
sorry.
so you're coming from so you're assuming that sort of your Hamiltonian is given in terms of sort of pairwise interactions.
Yeah, which I guess you can't assume.
No, so that's so pairwise interaction, let's say, between atoms or nuclei. So so in this case, usually you have your potential energy surface given in some kind of analytic expression in terms of the coordinates, and you don't have an electronic or a Hamiltonian, and a quantum mechanical Hamiltonian is here, right?
Right.
If I understand this correctly.
Is it the nuclear Hamiltonian you calculate the expectation value of the nuclear Hamiltonian over the electronic wave function?
You mean in expression 6?
So in the expression 7 or 6.
Yeah, so this would be an electronic Hamiltonian. Therefore, I mean, it has the subscript E for electronic.
Okay.
If we just go to...
Sorry, yeah, I didn't see that.
If you just go to... where is it? Yeah, here, right? Here in equation 4, it's defined. It would be the... yeah, it's, you know, usually the usual terms that you have in an electronic Hamiltonian. If you do classical MD, then usually you have your potential energy surfaces given in explicit form with respect to all your nuclear coordinates, and then you can calculate the forces usually analytically. This is why classical MD is so fast.
Yeah. But here you would have to. So VNN is given analytically, but VEN is the thing that's calculated through electronic structure calculations.
One has to be a bit careful. So if you do classical MD in the end, you don't have any electronic terms anymore.
I wasn't talking necessarily about doing classical MD in the end.
Okay. Mm-hmm.
I was talking about using pair potentials, or sorry, not necessarily pair potentials, but calculating pairwise forces, but not from, but for you know, Born-Oppenheimer MD, analogous to what you do in classical MD usually, as you do in many body force. Oh, yeah, okay, sorry. I think my question.
It's fine. I'm not quite sure where you are going to now, but
okay, sorry.
Sorry. Yeah, I mean, okay, so maybe in terms of the lambda can be sort of any. It can be a nuclear coordinate, or it can be a function of a nuclear coordinates, or function of nuclear coordinates, if you like.
Yeah.
Including distances.
But that might in practice be quite tricky to actually calculate the forces that way.
Yeah,
with
you never do it.
distances.
You always compute basically forces acting on the absolute position of the nuclei, and then you move along rather than doing some complicated sort of, let's say, coordinate transformations.
Yeah.
Are you doing, because you're asking, I mean, are you doing some kind of gas phase scattering calculation or something like that?
No,
You would usually transform the from the coordinate, you would use internal coordinates, right? Oh, this is probably where you're coming from, right? So when you do electronic structure calculations, you probably use internal coordinates, right?
I'm mostly coming from a classical molecular dynamics background,
Okay.
but we are looking into sort of potentially using electronic structure, but as well, it depends on. So it's actually really around nanoparticles and things like that, but I don't know if that's.
But I mean,
it's not going to be competition possible.
Yeah, if you want to, calculate the gradient along some sort of, let's say, other kind of definition of coordinates of your system, like internal coordinates, you can always do a variable transformation, and then so from Cartesian to your internal, and then you have to transform your gradients accordingly.
Okay.
But then usually all these MD codes, classical as well as ab initio MD codes, they usually calculate the gradients in terms of the Cartesian coordinates. And then sometimes when you actually have to do that, the transformation is when you do constrained molecular dynamics, where you constrain different bond lengths. For instance, as you know, like if you do classical water MD simulation, very often the water potentials, they are for rigid water molecules.
Yeah, doing that now actually.
Yeah, so then it becomes more complicated, because then you have to transform, calculate the force along the bond vectors, and then subtract it so that the bonds remain fixed.
Okay.
So yeah.
Okay. All right.
But once you have the Cartesian gradients, you can then calculate the gradients for any function of these Cartesian gradients.
Okay.
I don't know. Maybe.
Nice. Okay. So thank you very much. Sorry.
No, it's good. It's very good that you're asking. This is what we're here for. Okay. Right. Are there any other questions on this? No. Okay, then I'm trying to sort of establish a link to what you have heard before in the previous lectures, so that you see that actually all these things are not sort of some separate topics, but they all sort of talk to one another, and one topic sort of uses part of the other topics. And so essentially ab initio MD is, if you like, a combination, a synthesis of let's say sort of classical MD for the nuclei, and density functional theory for the electronic description. And so this is just a slide here that sort of summarizes what you heard before. I hope that you sort of that the notation is not too different from the notation that you used before. Yeah, that's just a summary of the equations, where you go from electron density to electronic energy in density function theory. Is this clear? Yes.
Hi, Jochen. Could you just remind me, these cone-sham orbitals, they're like the electronic states which have been constructed out of plane waves, right?
Yeah, so these cone-sham orbitals, you can construct them, if you like, in any basis set. So that could be plane waves. That could be Gaussian basis set. That could be even a Slater basis set. That could be wavelets. That can be any well, let's say set of orthonormal function. But I mean, in the popular codes, like for instance VASP or let's say quantum espresso. I'm just talking about this because the likelihood that one of you is using those codes is probably high. So these Conjam orbitals are a linear combination of plane waves, yeah. Whereas in Gaussian or in CP2K, it would be well, CP2K is a dual basis set code, but it would be a linear combination of different Gaussian functions.
Okay, thanks.
Mm-hmm. Yeah. Okay, so there is it's a bit weird because in DFT, I mean, there's the density, but essentially still you express the density in terms of orbitals. And that has to do because we don't have an expression for a good expression for the kinetic energy, for the electronic kinetic energy in terms of the density. Therefore, basically, Cohen and Sham introduced again orbitals, Cohen-Sham orbitals, and non-interacting orbitals. We know what the kinetic energy is, which is this thing, right? The Laplacian acting on the orbitals, summed over all orbitals. Okay, so this is the classical electrostatic interaction energy of the density with all the nuclei, with the positively charged nuclei, the usual Coulomb interaction between all the electrons, and then the correlation energy between the electrons and the difference between the exact kinetic energy of a given density rho and the one that you see here. These two contributions, they are sort of folded into that exchange correlation functional. And okay, so that's clear. So you probably have heard this now many times the last couple of weeks. And all the approximations, so it's formally exact, all the approximations go, of course, into the exchange correlation functional. So that is a bit of a bin, basically. So all the terms that you don't know, you have been put in there. And all these acronyms, PB, BLIP, and like range separated hybrid, they all refer to different approximations of this exchange correlation functional. But in the end of the day, it's sort of a functional of the density or even of the gradient of the density. Some people put some Hartree-Fock in there as well. It forms a functional, and this functional is minimized in the ground state. To get the ground state energy, this functional needs to be minimized with respect to all the densities rho that integrate to n electrons. Okay, and this you have to do in MD simulation, in Born-Oppenheim MD simulation, you have to do for each given configuration R prime here. Okay, so you have to do this for each time step. So this is why ab initio MD is very expensive, because you have to do a sort of a single point calculation at every MD time step, and usually MD time steps are in ab initio MD 0.5 femtoseconds. So now you have to do this minimization essentially 2,000 times in order to propagate your nuclei for a picosecond. Okay, so that's density functional theory. I hope the notation is clear. Okay, so a little bit more. So okay, so that's nothing more than saying you have to solve the Conjam equations, and you can write them down in different ways. Now, it's also important to note that the energy that you get from solving these Conjam equations is of course not equal to the exact ground state energy, which is E0 R prime. It would be exact if that exchange correlation functional would be known. but it still gives, you know, for the functions that we have, is a very good approximation, and it usually gives pretty good forces as well. So this is now the synthesis where you combine molecular dynamics with Concham DFT. So these are now the combined equations. You do the minimization for the electrons, and you calculate then the nuclear derivative to get the forces. And for this, you use this Hellman-Feynman theorem, now here written down in terms of the Concham Hamiltonian and the Concham wave function that you build from your self-consistent Concham orbitals that minimize your energy functional. And again, you can drag this gradient into your expectation value. And so basically this gradient, I mean, what is this gradient here? Well, it's quite simple. It just has basically two terms, because it only involves the interaction of the electron cloud with the nuclei. So this is this term here, right? This is a non-vanishing derivative with respect to the nuclei, right? So that's just a Coulomb. A Coulomb, 1/r minus r capital square times rho r integral. So that's easy to calculate, right? And then just this one here. This is just a Coulomb, a sum of Coulomb terms. In this case, Coulomb forces if you take the derivative. And that's it. So this is why it's very cheap to calculate the forces once you have the self-consistent, those self-consistent Concham orbitals. Okay. So there's also in the community maybe a sort of people differentiate between, or should probably differentiate between density functional based MD and ab initio MD, but some people don't differentiate and think it's the same. Where it depends whether you think that DFT is an ab initio method or not. That probably depends on the functional that you're using. So yeah, it becomes a little bit philosophical here, but yeah, in common use of both acronyms. So okay, so that's all about the theoretical part. Any questions? Okay, so that's all very dry and mathematical maybe. So maybe let's have a look whether I can get this animation to work. Let's remove this. Okay. Okay, so you see, are you seeing? You probably see a water molecule now, right? I hope so, at least. Okay, so I said, so why do you go through that sort of very expensive calculations? Ab initio molecular dynamics, because you can simulate chemical reactions that you can't really do with classical MD, so this is actually a simulation that I did myself a long time ago as a postdoc. So that is what is simulated here is the attack of a formamide molecule, which you can see here. So formamide, I don't know how many of you are chemists, but this is a carbon, and this is a nitrogen, so carbon, nitrogen, and this is a oxygen here, and the hydrogen that you don't see. So this is a model system for, let's say, hydrolysis of a peptide bond, right, in proteins. Hydrolysis of peptide bonds in alkaline solution. And what you can see here is that you have, actually you're in the middle of the reaction here. So what you have here is that you have this formamide in aqueous solution, and then you have a hydroxide ion, OH minus, that's basically also in that solution. And what you see here is the attack of a hydroxide molecule onto that carbon of the formamide. And so what's happening there first, before the attack, the CO bond is a carbonyl bond, right? And as the OH minus attacks, the carbonyl bond CO double bond becomes a single bond, and the oxygen becomes 1 minus, and then you can see how essentially a hydrogen gets partially transferred to that O minus, because the O minus becomes very basic. So at the same time, you see that this CO, the CN also changes character and becomes a pyramid. So so the movie that I show here essentially tells you a lot about the let's say mechanism, and it will show you how much things fluctuate actually in real time in these aqueous solutions. And so these simulations can also be used to calculate activation barriers and rates. So I hope this thing works. Oh no, it's the next one in the end. These are the ones that I showed last time. This one, screen sharing. Okay, so this is the so here, this is the beginning where the OH minus. So this is the initial state, and then the OH minus comes. OH minus comes and attacks this this bond here, and you see that at the beginning. Maybe I should play it again. At the beginning, the molecule is sort of planar, and as the OH minus attacks, the molecule becomes sp3, as you can see, and that nicely goes from sp2 to sp3 hybridization. What you would expect actually from standard organic chemistry in the end, but it's actually nice to see that this also comes out from ab initio and desimulations. And so you see that, so this is an aqueous solution, so you see that there is, it's a lot of motion that's going on. So the whole movie is probably in the order of maybe a picosecond or two or something like this. Okay, so that's an application of ab initio molecular dynamics, simulation of chemical reactions. Maybe then I should talk a bit about the second slide. Oh, I don't have this here. The second set of slides about the StatMac. Yeah. No, this is. Oh, here. I'm still not proficient with Zoom. All right. So that's the statistical mechanics. So in the end, you would like to do. So why do we actually do MD simulations? Because we want to calculate some observables. You know, that could be energy, total energy, free energies. Free energies are very important because free energies are related to equilibrium constants, and they tell you whether things happen or don't happen. You can use MD simulation to calculate the kinetics, which basically tells you how fast things are happening. And there are several techniques that you can use to do that. Very often, like with classical MD, I mean, with von Oppenheimer MD these days, maybe you can simulate maybe 100 picoseconds, things that are happening on that quite fast time scale. With classical MD, you can probably go these days for small proteins, let's say, to a couple of 10,000 atoms. You can probably go routinely to let's say microseconds, if not maybe 100 microseconds, something like this. So many times longer. Very often this is still not long enough, because the process that you would like to look at, for instance, I don't know, like protein folding or some very slow chemical reaction, is happening on the millisecond time scale or on the hour time scale. And then you have to use special tricks to speed up the sampling phase space. And this is something that that we don't discuss here, but you will hear about this in the next lectures, I assume. Okay, so that's a bit sort of an overview over the importance of StatMech. And just a question again, there anything you would like to ask about time averages, about the ensemble averages, how they are connected? No? Okay. Yeah, so as I said, in these time-stepping algorithms, that just gives you a trajectory, that's a sequence of configurations. So as you've seen in that movie, I mean, that movie consisted of an ab initio MD trajectory of probably, let's say, maybe 10,000 frames, right? In that movie that you've just seen. So you have solved you have minimized the density functional for 10,000 different configurations, and that each time you calculated the nuclear force on each of these atoms that you have seen, and then you have moved them in time according to the velocity Verlet algorithm. So that's actually the algorithm that was used there. Every electronic structure calculation takes maybe 10 minutes. So you can now know why we need supercomputers for this kind of simulations. The time averages, so if you want to calculate an observable along these trajectories, obviously you would have to time average that, and that's in that first slide. It's well, that's quite simple. If you just solve the Newton's equation of motion in the end, then you get this time average, you get the trajectory, and you get this time average. And so the question is then, how is this time average related to, let's say, the ensemble average that you have in statistical mechanics? And as we know, in statistical mechanics, you have different ensembles. You have the NVE ensemble, which has constant energy. So that means that the system is only allowed to have only one value of the total energy. Then you have the NVT ensemble, where you have where the temperature is constant. So that means that the total energy can vary, but not sort of arbitrarily, but according to a distribution. So now in the NVE ensemble, you describe these ensembles with probability densities. So that's the probability for the system, to be at a given point in phase space. And in the NVE ensemble, you can only be at points in phase space that have the same total energy. So therefore you have this delta function here. And one of the first principles of statistical mechanics is that the probability to be in any one of these states is the same. Therefore, the probability density is proportional to the number of states in a system that has this given total energy E. And the partition function is just the sum over all these points, if you like. The hypothesis is that during the MD simulation, MD simulation in solving the Newton's equation of motion also generates a trajectory, and each point of the trajectory has the same total energy. So because the Newton's equation of motion is energy preserving, so you can show this. You probably have shown this a long time ago in classical mechanics. So Newton's equation of motion, the total energy doesn't change in time. So therefore, the question is whether you actually sample the NVE ensemble in molecular dynamics. And the answer is yes for most of the systems. For most of the systems, you have this ergodic hypothesis where the time average you obtain from MD simulation in the limit of infinitely large trajectories is the same as the ensemble average in the NVE ensemble. So that's when you do MD simulation and you're calculating a property in the NVE ensemble. So this is usually what you assume is the case, and there are exceptions, of course, especially for glassy systems, where when you do MD simulation where they do not sample the NVE ensemble. The NVT is probably sort of also quite familiar to you, or most of you. So there you consider your system that you want to simulate connected to a heat bath. And so energy between the system and the heat bath can exchange. And it turns out that, in StatMech, the number of realizations is maximized when the total energy, when the energy in your system is Boltzmann distributed. Okay, so this is so you can derive that Boltzmann distribution. You probably have done that in StatMech. Instead of each point in phase space is not anymore sort of equally populated if it has the same total energy. So here actually every point in phase space is populated, but only proportional to the Boltzmann factor. So that is that's written down here, where also the partition function that I call omega is just the the sum of all the Boltzmann weights over in phase space. And now, how do we calculate then expectation values in that ensemble? So you just have to multiply each observable at a given phase space point with the Boltzmann weight and integrate the overall phase space. And for a long time, it was not known how to sample the NVT ensemble with molecular dynamics. Obviously, you cannot just solve Newton's equation of motion because that samples the NVE ensemble, assuming ergodicity. And okay, I leave the temperature concept out here. So so then NUSE came in the early 80s and then derived an algorithm that allows you to sample the NVT ensemble using MD simulation. But as you can see here in this equation, it's not only just simple Newton equation, but you add a friction term. So friction term is whenever you have an additional force that's proportional to the velocity. It's like the friction of a car, if you imagine. So, you know, the faster the car, the higher the friction force. So the friction coefficient here, zeta, I think is that the name of that symbol, is proportional to r dot, to the velocity. And interestingly, this friction coefficient itself is not a constant, but it actually changes in time during the simulation in this peculiar way where the velocity, as the change of that friction coefficient with time, is proportional to the difference in the total kinetic energy of the system minus twice the average kinetic energy of that system. And Q here, for dimensional reasons, has the dimension of a fictitious mass. It turns out that the you know, if you do MD simulation with these modified equations of motion, then so you can show that you are sampling then the NVT ensemble. So each point in phase space is sampled according to the Boltzmann weight of that configuration. And so yeah, you can show this, and you can also connect the meaning to the sign of the zeta coefficient. So if this zeta coefficient is basically positive, so that means that you know, that you get some cooling, and if it's negative, you get some heating. So you can quite nicely show that by taking the derivative of the Hamiltonian with respect to time, and then you see that. So in normal classical Newton dynamics, this time derivative obviously would be zero because you're preserving a total energy in time. But in the NUSE NVT dynamics, it's not zero. And so the picture of that, if you like, is shown here on that right-hand side panel, where in the phase space P and R, I just show surfaces, hypersurfaces of constant total energy. So that means that on these surfaces, P square over 2m sum over all particles plus potential energy V is the same on all these points. So this is sort of a hypersurface for an energy, total energy zero, for a higher total energy, and for an even higher total energy. And we know that the probability for the trajectory to be on each point is equal to e to the minus beta e, the Boltzmann weight. And so that means that in the NUSE dynamics, the time that the trajectory spends on each of these surfaces is proportional to its Boltzmann factor. Yeah, so it's most of the time it's of course in the ground, in the lower energy states, and the higher the energy, the lower the energy, the lower the probability to be one of these higher excited states. Okay, whereas if you do just NVE or just simple Newton dynamics, you would just always remain on one of these surfaces. Right, so that's a lot of talking. It's 2 o'clock. Are there any other questions? Are you still around? Actually, I don't know. I haven't seen that. How many of you are around? 12 still. Okay.
No more questions. Thank you.
Yes. Hello.
I was just saying I don't have any more questions. But thank you.
Okay. Right. Yeah. Yeah. Okay. So okay. If there are no other questions, then I suggest to close this session, and then I think next week onwards, I think you continue with ensembles and I think with enhanced sampling methods. All right. Okay, thank you very much. Bye.
Thanks a lot, Jochen.
Bye-bye.
Thank you.
Bye.
Thank you. Bye.